Where's the traffic light? Oh, there's traffic. Good afternoon, everyone. So the work I want to share today has kind of built up over the last 6 months and includes work I've done on my placement, as well as most recent campaign, sort of February, March. So just some background context. VOCs, which come from both biogenic and anthropogenic sources, when they're emitted into the atmosphere, they can undergo oxidation via oxidants such as hydroxyl radicals, ozone, or NO3. The products of these can be of a lower volatility than the initial compounds. This is an LVOC. These LVOCs can partition into the aerosol phase, either by nucleation and the formation of new particles, or they could condense onto primary aerosols, such as from a car exhaust, and then you get particle growth and fewer larger particles. Every element of this very simple diagram is far more complicated. The types of VOCs you have in the atmosphere, the humidity, the temperature, what oxidants you have, all of these will contribute to making different secondary organic aerosol. And so we want something that is reliable and something that we can use on a wide range of applications to study SOA, secondary organic aerosol formation. And so my project has focused on this, which is the Ducati oxidation flow reactor, or DOFA, and my job has been to characterize it. And in its simplest terms, it is a kind of quartz reactor tube with 12 UV lamps. We use very high ozone concentrations, magnitudes higher than in the atmosphere. We add humidity and we kind of shine these lights. We generate lots of hydroxyl radicals, and we get days, if not weeks, of atmospheric aging in as little as 30 to 40 seconds. Potentially, that's really useful, that you can kind of accelerate these atmospheric processes in the lab. But we need to make sure that it's reliable and relevant to the atmosphere. So in Manchester, my project has been to characterize the OFR, and one element of this has been to compare it to the Manchester aerosol chamber, which is kind of a more established and kind of understood piece of SOA formation equipment. We know it's relevant to the atmosphere. It kind of more slowly oxidizes things. And so I've been trying to work towards this comparison as part of my project. The comparison can be as simple as just adding alpha-pinene to both bits of equipment. We oxidize them under similar conditions, and we characterize the secondary aerosols that come out. Ideally, they'd be the same, but hopefully they're at least comparable. But there's a lot of factors and kind of differences between these two reactors that make that more complex. These factors can range from anything such as the OH concentration, its magnitude higher, the ozone you have to add to achieve those concentrations, the number of lamps you have, the types of lamps, the configuration of lamps, the fact that you're comparing a batch reactor, the chamber, versus a continuous flow reactor, and many other things. Some of these we can't change. They are just inherent to the design of the reactor. If we were to try and change them, we're no longer comparing the DOFA with the chamber. So we can kind of discount those for now. If we can understand them, that's great, but we can't change them. Other things, such as the number of lamps or the ozone, we understand the effect they have, and we can control them. We can turn down the number of lamps, we can decrease our ozone concentration, and we can try and match these up a bit better. And that left us with aerosol seed, which is something that we were consistently adding to the chamber, but we weren't adding it to the OFR. And I asked the question, kind of, what difference does it make? And that led us down quite a long rabbit hole, which is the basis of the next 15 or so slides. So my placement, the kind of conditions of the placement, it was going to be up to 3 months. I'd be working with my sponsor, Ducati, in Tampere, Finland. We wanted to do something that was distinct. As much as I would love to spend 3 months in Finland on a holiday, if I'm going there, I need to be doing stuff I can only do there. Otherwise, I may as well have stayed in Manchester. And we also had the opportunity to collaborate with Tampere University, who was based in the same city. So we had access to a DOFA at Ducati, and we had the ZAR, the Tampere Secondary Aerosol Reactor, and that is the kind of pre-commercial predecessor to the DOFA. So it works on the same concept, it's just a less commercialized version. And while searching through the literature on a way to compare these two reactors, I found this figure from Lam et al., where they had a similar question. They were trying to compare an OFR to a chamber, and they asked the same question of what happens with the aerosol seed. And I thought of the wonderful idea to not copy, but kind of be inspired by this figure, where here they've used two different sulfur aerosol seeds in the PAM chamber, which is a different OFR, and they've got some idea of composition and some idea of SOE yield. So our plan then was to oxidize two different VOCs and a mixture of the two. So I was going to use alpha pinene and toluene, two that I had experience with in Manchester and were relevant to my work. I was going to ramp up the ammonium sulfate seeds that I was adding to the reactor to try and get that x-axis on the figure. We'd measure the mass, the number, the size, and the composition of our secondary aerosol to try and get that y-axis. And we were going to do this in both the DOFA and the ZAR. The setup for this is a relatively simple setup of just having a nebulizer for our seed. We have a VOC saturator to inject our alpha pinene or toluene. This is just a freezer with two glass bottles, and we put a really low airflow through it. And then we have our sample conditioning, and then our OFR that we're sampling through, and all the different instrumentation. Flame ionization detector, the FID, and the Fourier transform infrared spectrometer, the FTIR, that was used to measure the VOC concentration that we're inputting. And then we have LP, CPC, and EAPS for our kind of aerosol mass number size. Oops. Go back. And then we had gas analyzers to kind of measure ozone, OH, which we can work out, and the AMS for aerosol composition. So just looking at toluene as an example, and I stress this is really rough data. This is just kind of the initial checks that I did working through the work. It's only LP data. The lines are just there to guide the eye, so don't read too much into them. But this is for the DOFA that we had in Finland, and the important thing is that you can see as we kind of increase that seed concentration, the number, the blue trace, starts to decrease. We're suppressing new particle formation, and we start to see aerosol growth. We get a similar graph. Well, sorry, for the mass, it's kind of the opposite. You start low in mass, you've got lots of small new particles. As you add seed, your mass ramps up. For the ZAR, we get a similar graph. Everything is slightly shifted though, and I'll overlay them in a second. But I guess it was reassuring that we're seeing the same behavior with that suppression of new particles and the growth in mass. Just overlaying the number concentration for both the reactors, we can see that the seed concentration required to completely suppress that new particle formation, that kind of dip at the bottom, is much higher in the DOFA. It's about 3 times as much. They should be the same OH concentration, the same amount of aging. It should be the same amount of VOC. So it was surprising that we're having to add so much more seed to suppress that new particle formation, and that we're seeing that kind of that initial number on the y-axis is much higher as well. But again, it's rough data, and there's a lot to kind of interpret from it, and for us to refine on the analysis as well. And this isn't even to mention any compositional information and anything to do with the mass. So upon returning to the UK, I kind of adapted the setup slightly for the instruments that we had. So I didn't have EAPS, didn't have FTIR, FID, or anything like that. But I did have access to an iodide mass spec and a Vocus PTR mass spec for our VOC kind of concentration and consumption. So just a slight adaptation. And I ran through the same program, and I'll just show the toluene again for the DOFA in the UK. We see the same characteristic shape, which is really reassuring, but the absolute numbers are kind of different again. So overlaying it with the previous two you've just seen, again, we're much higher seed concentration to suppress new particles, and we're much higher number initially. So there's lots to kind of question in that. And I have my suspicions about where that's come from and some dilution ratio issues and things like that. But really, it will hopefully be ironed out as we go through the data. For the chamber, so we have compared to the chamber, but I don't have anything to show yet. But I ran 4 alpha-pinene experiments, 0, low, medium, and high seed. So hopefully we can plot that onto a similar graph as the previous. Got the compositional physical data. It's just the fact that each chamber experiment takes a whole day. It's a lot harder to get that initial plottable information versus an OFR, which is continuously sampling. So in conclusion, I guess the main takeaways, I've taken 2 DOFAs, the ZAR and the MAC, and I've done this comparative study across 2 institutions. We're determining how consistent the DOFA is within its product range, which is quite important for a commercial instrument. We're developing the understanding of effects of aerosol seed and SOA. This is important for us to kind of make future comparisons. And yeah, my future work is basically analyze the data I've got, determine if I need to repeat anything. I've got some time in August, so hopefully everything I've collected so far is usable. Hopefully work towards publication. And we do have data from more complex examples like a diesel engine, but it's kind of limited or held back at the moment by this question of the aerosol seed. So by ruling that out, it kind of opens more comparisons. Thank you for listening.
Stephen, do you have any questions? I was looking at you now.
Very nice. Nucleation is amazingly sensitive, of course, to conditions, but I would expect the ratio of the collision frequency with the chamber walls, the OFR walls, to the, not the mass, but the collision frequency with the aerosol, the condensation sink, to be the crucial parameter. So if you looked at that, so slight shifts in the size distribution, or slight shift, if the SAR and the commercial instrument have the exact same Reynolds number, et cetera, et cetera, et cetera, or could that be what's going on?
So it's kind of top of the list. I've got a long list of kind of points to iron out, and this is quite up there in terms of how our size distribution is changing, especially with like our input seed as well. We use 2 different generators between the UK and Finland. There are some differences with kind of the shape and size of the reactor between the DOFA and the ZAR. It's a slight difference. One of them has a slightly more conical end than the other. But yeah, it's something that we are looking at, and Mika Dalmassa, who I was working with in Finland, he was very keen to look at changing condensational sink and how that's affecting it. We had planned more work while I was there, but 3 months seems a long time until you get to it. So we ran out of time on that, but hopefully, yeah, it's on the list.
So I hadn't really ever, it's been a while since I looked at this, but I found it really interesting how you can vary the C concentration. You can get so much data in varying the C concentration. So I'm presuming I'm not aware of other studies which have done that, probably I'm way off here, but that must help you really consolidate our understanding of the kinetics of the process, where you can vary the C concentration over such a range. Can it?
Can it in terms of giving how much information you can get?
Yeah, how much information can you get? You have some really quite nice shapes and dependencies in that.
That was a big thing for us, was kind of capturing that suppression as much as possible. It was interesting. So the OFRs are really good at that you can change a setting within 2 minutes. You've got stable data, a whole new set of conditions. Whereas for the chamber, we had to know going into the day what we wanted to do, and then you don't know at the end if it was any good. So that was the benefit of the OFRs. And I think there's a lot in there that's quite interesting, because kind of as we come across on the x-axis and we bring that number down, it's less of a shift in the distribution and more of kind of an increase in a new distribution and a decrease in the existing. So yeah, there was a lot of back and forth about which part of that x-axis we should really hone in on, and it was kind of decided from the turning point to the lower rather than kind of just ramping seed up for the sake of it. But yeah, hopefully once we get the composition on it, it'll be a lot more interesting as well.
Great. Thank you very much.